We've got the graph of secant up here on the board. Suppose I could label that. Secant is the reciprocal of cosine. So I drew cosine as this dotted red curve. And wherever cosine is 0, that's where secant has its vertical asymptotes. And then we basically just flip the bumps, is how I think of that graph. All right, we're going to restrict the domain to get an invertible function. And as I mentioned, there are two accepted definitions of the way to do that. So there are two different accepted definitions of inverse secant out there. So for many of you, this is going to be a change. If you took pre-calculus here at Saddleback using the Miller textbook, if you took pre-calculus last semester with me, I taught you a different definition of arcsecant than I'm going to teach you now. I warned you that that was going to happen because I knew that was going to happen, but different textbooks use different definitions. That's kind of annoying. It would be good if mathematicians could just get together and agree on the definition of inverse secant. But we can't. So, very important that you know that for secant and also for inverse secant, the definitions of their inverse functions are not standard. There are two standard definitions out there. Really important as community college students that you know that, because I know the majority of you are planning to transfer to a four-year school, and I'm guessing most of you aren't making the decision about where to transfer based on which definition of arcsecant or arccosecant they use. So it's possible that just like the definition for many of you changed going from pre-calculus to calculus, it's going to change again when you transfer. And it does affect the formula that we get for the derivative. So we're going to work through this one together. All right. I do know that I always like to choose the standard copy of quadrant 1, the interval from 0 to pi over 2, which corresponds to quadrant 1 and my acute angle. So I'm keeping that, okay? I can rule out quadrant 4 because in quadrant 4, secant is also positive and I don't want to repeat my positive values. Now, with all the other functions we've done so far, we ruled out quadrant 3 because it's not adjacent to quadrant 1, and that was going to mean we wouldn't get a connected piece of graph. But if I look at the graph of secant, there's no way I'm going to get a connected piece of graph when I restrict the domain, because the positive part and the negative part don't connect. Secant does not take on any of the values between -1 and 1. So the advantage of having an adjacent quadrant is lost. We're not going to get a connected piece of graph. Now, some textbooks do still choose quadrant 2. The advantage there is that when we restricted the domain of cosine to then get the range of arccosine, we used quadrants 1 and 2. So the range of arccosine was everything from 0 to pi. If we were to choose quadrant 2, we would basically be choosing the left half of this upside down u, and then we would restrict the domain to be everything from 0 to pi, excluding pi over 2, because of course that's not in the domain of the original secant function. Okay, that's what we did in pre-calculus, at least if you used the Miller textbook that most of us here at Saddleback use. Okay, the advantage then is that the range of arcsecant is almost the same as the range of arccosine. However, this textbook makes what I think is the better choice. It chooses an interval corresponding to quadrant 3. So instead of choosing the left half of this upside down u, we're going to choose the right half of this upside down u. It is not at all obvious why I think that's the better choice. It's going to become obvious when we calculate the derivative. So the function that we create is going to look like so. We get the right half of this u, and we get the right half, So this is pi over 2, this is 3 pi over 2. We also get the right half of this upside down u. So this is y equals secant of x, where x is in the interval from 0 to pi over 2, including 0 because secant's defined there, but not including pi over 2 because secant is not defined there. Union pi to 3 pi over 2. Again, including pi because secant is defined there, not including 3 pi over 2. This is an invertible function. This is the function we're going to take the inverse of to define the inverse of secant. The other choice that's considered acceptable in the mathematical world would be to choose the left half of this upside down u. So then it would just be from 0 to pi, excluding pi over 2. Problem 64 in your text, which is an even numbered problem, but it's one that I assigned, acknowledges that there are these two different definitions and has you figure out what the derivative is in the other case. Good to know because you don't know which definition you're going to be using as you move on and transfer. Okay, so if I invert this, the definition that our book uses is that y equals arcsecant of x is the inverse of this. So that means that x is equal to secant of y, and y is in the interval from 0 to pi over 2, union pi to 3 pi over 2. Okay, now because this one's a little bit strange, because we've got two accepted definitions out there, I'm going to work through this one with you, and we'll talk about when that choice that we're making to go with what I think is the better definition, using quadrant 3 instead of 2, where that makes a difference. Okay, so I'm going to start by just copying this up here. X equals secant of y, with the restriction that y is in the interval from 0 to pi over 2, union pi to 3 pi over 2, being careful to use appropriate parentheses or brackets depending on whether the endpoint is included or not. All right, so we take the derivative. Derivative with respect to x of x equals the derivative with respect to x of secant of y. All right, derivative of x is 1. Derivative of secant is secant times tangent. And each one of those gets a y. So it's secant of y times tangent of y. That's the derivative of the outside part. And then multiplied by the derivative of the inside part, which is y prime. So we solve for y prime, and we get 1 over secant y times tangent of y. And we want to try to get that in terms of x. Now, one of these factors we already have. Secant of y is x. So I can say, okay, y prime is 1 over x times tangent of y. But now I need to try to get tangent of y described in terms of x, and I know that I'm going to be using my Pythagorean identity. Now again, you may have the Pythagorean identity that relates tangents and secants memorized. If not, you just start with sine squared y plus cosine squared y equals 1. I know that tangent and secant both have cosine in the denominator. So I divide through by cosine squared, and we get tangent squared y plus 1 equals secant squared y. Now I want to try to solve for tangent of y. So tangent squared y equals secant squared y minus 1. I'm going to take the square root of both sides. Square root of tangent squared is not tangent. It is the absolute value of tangent. And that means that tangent of y is plus or minus the square root of secant squared y minus 1. Which sign I choose depends on whether y is an angle whose tangent is positive or whose tangent is negative. And that's going to depend on which quadrant we're in. Now, with our choice, this corresponded to quadrant 1, and this interval corresponded to quadrant 3. Tangents positive in both quadrants. Okay, so here I can say y is in quadrant 1 or quadrant 3, so tangent of y is going to be bigger than or equal to 0, so I can choose the positive root. If we had made the other choice, tangent of y would have been negative in quadrant 2. And so we'd essentially have a piecewise formula for our derivative. We'd initially write it as a piecewise function, taking the positive root if y is in this interval, which would correspond to x being positive. Because if y is in quadrant 1 and x is secant y, x is positive. If y is in this interval, that would mean its secant is negative, x would be negative. So we'd have a positive sign in our formula when x was positive, we'd have a negative sign in our formula when x is negative. Okay. Here, it's nice. I get the same thing either way. And that's why I think this definition is the better one. Okay. So I can say y prime is 1 over x times tangent of y is the square root of secant of y squared minus 1. So that's 1 over x root x squared minus 1. Okay. That's the formula we get here. It's just this formula. If you were working with the other definition, you would start with a piecewise formula. I get this formula if y is in this interval, which corresponds to x being positive. I get that formula if y is in that interval, which corresponds to x being negative. Turns out you can then consolidate your answers because you get a negative sign in the formula when x is negative. So you're able to just put an absolute value around that x, and that gives you the formula if you use the other definition. But this is the one that we will be using this semester. Okay, you are assigned, though, question 64, to take a look at what happens if you use the other definition. And it's good to be aware of that because you might, at some point, be asked to use that other definition in a different class.